Okay, so today we'll be talking about mass transfer. And so it's very similar to the other transport phenomenon, like momentum and heat transfer. And so if you've learned one or the other, it should be very easy to pick up mass transfer. Um, but just to start, let's compare the three transport phenomena. So we have momentum, we have energy, right? So energy, and this is in terms of heat transfer, which I have a series on. So hopefully if you've seen some of that, this should be pretty simple. And then we have mass transfer. Perfect. And so when it comes to momentum, right, you might have heard of Newton's law of viscosity, which basically says that the shear stress, which is tau, is equivalent to mu times dv dx, right? Um, and so what this means is that the shear stress is actually negative. Shear stress is related to the velocity gradient times the dynamic viscosity. We have something very similar in Fourier's first law for heat transfer, where the heat flux, Q, is equivalent to negative K dt dx. So heat flux is equivalent to negative K. K is the thermal conductivity, and this is the temperature gradient. Now, you can expect that since these two are so similar to each other, we will see something very similar in mass transfer, and you would be correct. So in mass transfer, we have J, which denotes mass flux, and that's equivalent to minus D times dC dx, where obviously J is the mass flux, D is the diffusion coefficient, and dC dx is the concentration gradient. And so you can imagine that since all these equations are very similar, they're probably going to have very similar solutions, assuming that the boundary conditions are going to be similar as well. And we'll see that as we chug through problems in the future. Okay, so now that we've isolated mass transfer and said that, that it's very similar to the others, let's talk about it in specific. So when it comes to mass transfer, right, there's two main primary means of moving things um, from one side to another, right? And what are those two ways? Well, one is something you've probably heard of, diffusion, right? So this is like when you spray maybe like Febreze in one side of the room and it diffuses to spread across the entire room. But there's also something else, which is convection. And the interesting thing is, so this is for bulk flow. The interesting thing is that in mass transfer, you can actually get convection driven from diffusion. So this is a diffusion. It can actually cause convection to happen, which is a little bit different than what you see in heat transfer, where you can, isolate convection, and you can isolate, conduction. So conduction would be kind of a very similar, analogous to diffusion because this is from random molecular movement. All right, perfect. So now we're going to be first talking about diffusion, um, and we'll talk about the equations that govern it. So we have diffusion, and when we talk about diffusion, we mainly talk about the flux. That's what we care about. What is flux, right? Well, flux is basically the amount of, in this case, it's mass, so it's the amount of molecules, right, that's transferred per area, right? This is really important. This is per area and per time, right? So it's a rate over an area. And so if I write Fick's law of diffusion again, right, you'll see that it's J, right, for flux. It equals minus D, and this technically should be a partial derivative, so del C, del X, where C is concentration and X is position. So this is the diffusive flux. And I should also remind you that this is Fick's, actually, this is really important, so I'll change colors. This is Fick's first law of diffusion. Perfect. And this is very similar to Fourier's law and Newton's law. Now, you might have remembered that when we were talking about heat transfer, we introduced how there's dimensionless parameters, right? So there's something similar. I don't like this color. There's something very similar in mass transfer as well. So if you think back to our heat transfer, you might remember that we talked about the Fourier number, we talked about the Biot number, right? We talked about the Nusselt number, and you can imagine that there's very similar things in mass transfer as well. And so the first of them that we'll talk about is the Schmidt number. So what is the Schmidt number? Its short form is SC, and it's equivalent to momentum diffusivity divided by mass diffusivity. And how you would write that mathematically is nu, right? Nu is momentum diffusivity, and mass diffusivity is given by d. And so this is very similar to the Prandtl number, right? Because the Prandtl number was essentially momentum diffusivity over heat diffusivity, if you remember that in the heat transfer videos. We also have something else as a dimensionless parameter when it comes to mass transfer, and that's the Lewis number. And the Lewis number basically takes the approach of comparing the energy diffusivity to the mass diffusivity. And that's equivalent to alpha over d. And so you can see that we already have analogous quantities. We have nu in momentum transfer is analogous to alpha, which is analogous to d in mass transfer. So a lot of similarities. Okay, so now that we've stated Fick's first law and kind of given some understanding of how all these three transport phenomena is related, we can go ahead and start onto some problems where we talk about mass transfer. So the first thing to note is that when we were solving for heat transfer, right, we realized that the flux, the heat flux, is constant throughout, right? And it's the same thing that we're going to be looking at in these first couple problems where the diffusive flux is kept constant throughout the entire species or problem that we're looking at. And so keeping that in mind, we realize that J is constant flux. So now let's describe the problem that we'll be discussing. So imagine that we have a film, right? We have a film, and this film has length L, right? And there's a little cross section that we can, take in this and call that cross section delta Z. Now let me draw this a little bit more three-dimensional so you can get an understanding of kind of what this looks like. Oh, okay. Okay. And what this means is that the cross-sectional area, right? So this in the film, this cross-sectional area is going to have A. The value of it is going to be A. And so to label our axis, right, now we have let's call this the z-axis going this way. That means that at this location, z equals 0, and at this location, z equals L. Perfect. Now, the driving force for diffusion, as we talked about, is the concentration gradient. So we need to define what the concentrations are at either end. Kind of very similar to how we defined the temperature, the bulk temperature, and the temperature of the surface when it was heat transfer. So we're going to do the same thing over here. So let's say that we have a concentration gradient, C1 naught, right? The 0 defining that it's at z equals 0, and the 1 defining that it's species 1. And on z equals L, we have a specific concentration, which is C1L. We'll call that C1L. Okay. And we're going to assume that, on this side, it's a well-mixed solution on both sides. And you might ask, okay, well, what does well-mixed mean, right? Well, well-mixed basically means that there's not going to be any sort of concentration gradient that would, cause flow on this side, on this side. The only flow would be going through this film from C1 naught to C1L. All right. And so our goal with this is basically to estimate the mass transfer rate through the thin film and to calculate the concentration profile. Very similar to how we were calculating the energy flux through the temperature profile. And so when we do any one of these problems, we first want to set up the equation. And the relevant equation for any kind of transport is always accumulation, right? We look at accumulation, and that's equivalent to whatever comes in minus whatever goes out plus whatever is generated minus whatever is consumed, right? And so what we want to do is now convert that into relevant words for this problem. And so what does that mean for this problem? That means that accumulation is the rate of accumulation in our control volume, which is delta Z times A, right? Because delta Z is essentially this distance times this distance. So this is delta Z and this is A. And so that gives us this entire volume. Okay? So it tells us the rate of accumulation in delta z times A. Perfect. And that's equivalent to whatever comes in, which is the rate of solute the rate of solute entering at z, right? So if let's call this starting location, right? Call the starting location z, which makes this, right, z plus delta z, right? And so whatever comes in is the rate of solute entering at z. That means whatever is going out is the rate of solute exiting at z plus delta z, right? And in this equation, we basically don't have a reaction, right? We're assuming it's only one species, it's not reacting with anything, and so therefore, by conservation of mass, we can't have generation or consumption, and so these both go to zero. Perfect. What's our next step? Well, now that we've put it in words, we want to basically get the math for this. And so the rate of accumulation in the control volume is equivalent to basically, we want to get the mass, right? So how is the mass changing over time? That is essentially what we want. How do I put that in math? Well, how do I get the mass? If we look at the units, right, we have delta Z times A, which gives us volume. And how do we get mass from a concentration and a volume? We multiply the two, right? Because concentration is essentially mass per volume. And so this is delta Z times A times C1, the concentration of species 1, divided by dt. And so this is how mass is changing over time. Now let's go on to the rate of solute entering at Z. We have the mass flux, remember, from Fick's law of diffusion, right? So if we go up here, we know that the flux is J. And what is flux? Flux is the amount of molecules transferred per area per time. So what this would be is essentially the flux, right? We call this J1 for species 1, times area at Z, evaluated at Z. Okay? And so mass flux times area basically gives us the mass flow rate, right? How much mass is flowing through this Z cross-sectional area for any given time. So this is a rate, remember. Okay, and so we write something very similar for rate of solute exiting. And that would be J times A, Z plus delta Z. Because remember, the flux is always constant. We always have the same mass flux, diffusive flux. Perfect. So now we have this equation. What we can do now is we can cancel out some variables, and so we can notice that in this first derivative, d times delta z times a times c1, delta z and a is constant, right? These are constants. The only thing changing is the concentration, and so these are constants, which means that we can pull these out of the derivative, and so what we get is a delta z dc1 by dt is equivalent to aj1 z minus a j1 at z plus delta z. And so what we can do now is cancel out all the a's, right? What we now have is delta z times the concentration gradient is equivalent to j1 evaluated at z minus j1 evaluated at z plus delta z. All right. So now what we can do is we can divide both sides by delta z. We get dc1 divided by dt is equivalent to j1 at z minus j1 evaluated at z plus delta z. All of that divided by delta z, right? And so now if we take the limit of this right side, right, take the limit as delta z approaches 0, right? What we see is that this is essentially the definition of the derivative, right? I can write this as negative and this is negative. So to put that in proper terms, this is equivalent to minus j z plus delta z, right? Minus j1 at c, right? All of that over delta z. And so if I take the limit as delta z approaches 0, this turns into the definition of a derivative. And what I basically get, what I get is that dc1 over dt is equivalent to change in flux over position, right? Oh, and a negative, negative. All right, perfect. We also know, right, going back up from Fick's first law, that j equals minus d del c del x, or actually del z in our coordinate system here. So important thing to note, j equals minus d dc, or actually dc1 times dz, right? So if I take the derivative of this, remember the diffusion coefficient is just a constant. So different color. If we pick, right, so that means dj dz is equivalent to minus d squared c1 dz squared, right? And so continuing on down, right, we essentially get dc1 divided by dt is equivalent to d times d squared c1 times dz squared, right? And so putting this actually, we chose a 1D coordinate system, but if we were to do this properly with, let's say it was a three-dimensional system, what this means is that we would have to take the partial derivative, right? So this is del C, del T is equivalent to D del C over del Z squared. And this is also known as Fick's second law. All right, perfect. And so what I've basically done is taken the original, right, the original law, Fick's first law, which we already know is very similar to Fourier's first law, Newton's law of viscosity, right? We can probably imagine that mass transfer is very similar to heat transfer and momentum transfer. Um, and so we took this law and we basically created ourselves an equation that can describe transient mass flow with Fick's second law. And so in the next video, what we're going to see is how do we now apply this combination of Fick's first law and second law to actually solve problems, right? And then we're going to understand, well, the concentration gradient is what we always say drives diffusion, but is that actually true? And so we'll talk about that in the next video.